Welcome students to this second lecture of the series. In last lecture we had discussed the first linear data structure, that is stack, and in this particular lecture we are going to discuss the second linear data structure, that is queue. Okay, so queue is also a linear data structure. Okay, so queue is also a linear data structure. So elements in queue will also be organized in the linear fashion, or we say as in sequential fashion. So the elements will be organized one after the other. So imagine that this is our queue and size of this particular queue is suppose 5. Size of this queue is suppose 5. So this queue elements will be stored from index number 0 to say index number 4. Now as in stack we know that in the earlier video we have seen that one of the end is fixed and the other end is operational for performing insert and delete operations. Whereas in case of queue, both the ends are operational, right? So one of the end we call it as front end and the other end is called as rear end. So there are two ends in case of queue. One end is called as front end, whereas the other end is called as rear end. Okay. Now these both ends are said to be operational for different types of operations. Front end is an end which we basically use for performing the delete operation from our queue, and the rear is the end which we usually use to follow insert operation. Okay, so technically these operations are called as NQ and DQ in queue. As we know that in case of stack, inserting is called as push and deletion is called as pop. Similarly, in case of queue, insert is called as NQ, whereas delete operation is called as DQ. And there are specific ends that we use for performing this operation. You can imagine this queue data structure as our real life queue also. You all must be knowing that whenever you pay your fees in your college or whenever you go out for a movie, right? So we all stand in a queue, right? So this queue is operational from both the ends. The one who is coming new into this queue is coming from back side, right? So back is nothing but rear end. So we add the element from the rear end. And whenever a person comes in front and he is getting that service, right? He is buying that ticket, he goes out from the front end, right? So delete is happening from the front end. So in day-to-day life we come across various queues, right? Whenever we stand in a line, the same example you can visualize are all the applications of our queue, where the inserting is carried out from the rear end, which is backside, and we call this operation as NQ, and the operation for removing the elements is called as DQ, which is happening from the front end. Okay, now whenever we want to go for these operations, if I add one element, the first element will be added here. If I add the second element, it will be added here. When I add the third element, it will be added here. When I add the fourth element, it will be added here. When I add the fifth element, it is added here, right? Now in this situation I have done 5 NQs, right? I have done 5 NQs. The moment when my queue becomes full, and again if I try to perform in queue, now there is no space available, so we will be getting a phenomenon called as overflow. We'll be getting a phenomenon called as overflow, but this overflow is for queue, right? So a phenomenon in which the queue is full and user is trying to perform NQ operation, we go for queue overflow. Similarly, whenever our queue will be empty, say for example I perform a DQ. Now in case of queue, whenever I perform DQ, which element will be removed first out of this? The element which is present at front, right? Because 10 has come first, then 20 has come, then 30 has come, then 40 has come, and then 50 has come, right? So if a new element comes, it will be coming from the rear end, and if a element has to be deleted, it will be deleted from the front end. Are you getting this, right? So the element that will be dequeued first will be 10, then next element that will be dequeued will be 20, then the next element that will be dequeued will be 30, then next element that will be dequeued will be 40. Are you getting this, right? So the element which is getting inserted first is getting removed first in this data structure, right? And that's why we call this particular data structure as Fifo data structure. We call this data structure as Fifo data structure, which stands for first in, first out, which stands out for first in and first out. The element which is getting inserted first is getting removed first from the data structure. So we call Q as first in first out data structure. If I further continue to remove the elements, which will be the element that will be removed? 50, right? Now, now my queue is empty, right? I don't have anything to be removed from my queue. My queue is empty. Now further again, if I try to perform dequeue operation, now there is nothing to dequeue and still user is performing dequeue operation, queue is empty, then we go to a phenomenon which we call it as underflow. So as we have overflow and underflow scenarios for stack, similarly we also have overflow and underflow scenarios for queue, where the overflow scenario is dealing with enqueue operation and the underflow phenomenon is dealing with dequeue operation. So whenever we will write logic for these two, enqueue and dequeue, we will also be thinking of overflow and underflow, same as that of stack. Okay. Now we will also have third operation, that is traverse. Traverse operation is nothing but we are visiting all the elements one after the other. So suppose I have done 3 enqueues, 10, 20 and 30. Okay. So if I want to print all the elements, then I am going to print all the elements 10, 20 and 30. This operation will be referred to as the traverse operation. So I hope you have understood now the operations of queue. What is queue again? Just to revise, queue is a linear data structure in which both the ends are operational. The two ends are called as front end and rear end. The end that is used for adding the element or inserting the element is rear end, and the end used for deleting or removing the elements is front end. Operation for adding the element is called as enqueue. Operation for removing the element is called as dequeue. If the queue is full and still user is trying to perform enqueue operation, we get queue overflow. And if the queue is empty and still user is trying to perform the dequeue operation, then the phenomenon we get, that is underflow. And the third operation that we have is traverse, where we print all the elements of our queue. Now in order to implement this particular enqueue and dequeue logic for our queue, again we will have two approaches. One is static, which will be done with help of an array, and another will be dynamic, which will be done with help of linked list. So we will be discussing dynamic approach once we complete the linked list version in our lecture series, and in today's particular lecture we are only going to focus on the static implementation as far as array is concerned. So we are going to implement now queue statically with help of an array. Now in order to implement this queue, we are using two variables. Okay, because here both the ends are operation. So the two variables that we use are front and rear. Initially we keep both this front and rear to -1. Initially we keep both this front and rear to -1. As we have kept top as -1 in case of stack, which helps us to initialize our stack at the start as 0, as empty. Similarly, front and rear are also initialized to -1 initially to indicate that our queue is empty. So initially there is nothing in my queue, so I will remove all these elements. So my queue is empty, right? And both the front and rear are at -1. Now initially when I add the first element in a situation when my queue is empty, I increment front and rear both by 1. What I do? I increment my front and rear both by 1. So my front will become 0 and my rear will become 0. And I am going to scan the element at rear end. Which end we use for inserting the element? We use the rear end, right? So we are going to scan the element at A of rear. We are going to scan the element at A of rear. So what is value of rear now? It is 0. So we will scan the element at A of 0. And both our front as well as rear now are present at 0. Front is also 0 and rear is also 0. Now suppose again I perform second enqueue. Suppose I want to do enqueue of 20. Now my queue is already containing some elements, right? It is not empty. And in this type of enqueue, I am only going to increment my rear by 1 because the insert operation is going to happen at rear end. The only exception that we have is during our first enqueue. During our first enqueue, we are going to increment front and rear both by 1. But for all subsequent enqueues, we are only going to increment our rear by 1. Okay. So next time we are going to do rear is equal to rear plus 1 for the enqueue, and our front will remain 0. So in this you can visualize that now rear will be going to this part, right? So rear will be going here at 1, right? Now we'll be scanning the element at A of rear. So the next element 20 NQ will be going at this position. I hope you have understanding now how we are maintaining that front and rear for our NQ operation. Let us take one more example. Suppose I want to perform one more NQ operation, NQ of 30. So whether my Q is empty? No, Q is not empty, right? So Q is containing some elements. So in this case, we are only going to increment our rear by 1. So we will do rear is equal to rear plus 1. So rear will become 2. Okay. So if rear will become 2, then we will be adding our element at this particular position, right? That will be 30. How this has happened? Because our rear is now doing rear is equal to rear plus 1. So rear has reached to the position 2 and we are scanning the element at A of rear. In this case, front has remained at 0. Now again, if I add new element, what will happen? Rear is equal to rear plus 1. Rear will come here. We'll be adding element at this position. Again, if I add one more element, what will happen? Rear is equal to rear plus 1. Rear will be coming at 4. I will be scanning the element at A of rear, that is 50. Now again, if I am performing a NQ, so I am not able to do it. Why? Because already my spaces are occupied. So I cannot do rear is equal to rear plus 1 in this case, right? So if rear has reached 4, we assume that our Q is full and we cannot do an NQ operation. This will go to a phenomenon called as Q overflow. This will go to a phenomenon called as Q overflow. As in case of stack, if you remember, if top was becoming 4, we say that stack is overflow. Similarly, in case of a Q, if our rear becomes 4, then our Q is full and we cannot go for further NQ operation. In this case, we are going to represent the phenomenon called as Q overflow. Are you getting this, right? So while implementing the logic for NQ, what cases we will be considering? First, we'll check whether our Q is getting overflowed, right? So if our rear is equal to 4, then we will print to our user that Q is overflow. If not, then we are able to NQ. And again, while NQing, we have to check whether the Q is empty or Q is containing something. Because if Q is empty, then we are going to increment front and rear both by 1 to make it 0 for the first NQ. And if it is not the case, we are only going to increment our rear by 1. So these cases we need to check while performing our NQ operation, right? So to make it more clear, parallelly I would be writing code for you so that it will be easy for you people to understand. So let us go for the code in this case, right? So suppose we are implementing Q now using array. Okay, so we are having our main function and inside this we are declaring array of size 5. This is nothing but this is our Q of size 5. We will be having two variables, front and rear. Initially front will also be equal to -1 and rear will also be equal to -1, which helps us to initialize that our Q is empty. So we are initializing as Q is empty initially, right? Now again we'll have a menu driven program as we had in case of stack, right? So 1 will go for NQ, 2 will go for DQ, 3 will go for traverse and 4 will go for exit, right? So similarly we are going to do this as we have done in case of stack. So we'll have a do while loop, right? We need to take choice also. So I'll be writing this particular choice variable, that is int ch, and we are going to write the statements. Okay, so what is the statements that we are going to write? The first operation that we are going to write is NQ operation. The first operation that we are going to write is NQ operation. What is the second operation? Second operation that we are going to write is DQ operation. What is the third operation? Third operation we are going to write is traverse. And fourth operation that we are going to write is exit. So these are the four operations given to our user, and user will be selecting one of the choices, right? So %d, and that choice user will be entering in the form of ch, same as that of stack, right? Now based on what choice user has entered, we'll have 4 cases in our switch. We'll be having 4 cases where case 1 is now our case 1 will be NQ, case 2 will be DQ, case 3 will be traverse, and case 4 will be exit. And this will continue while your choice is not becoming 4. And we'll be having a default choice which will represent that user has entered a wrong choice. Are you getting this? Right? Now in case of NQ, what we check first, if our rear has become 4. As we had checked that if our top has become 4, then it goes for stack overflow. Similarly, if our rear has become 4, then we are going to print that the queue is overflowed. Queue is overflow, right? And if it is not the case, if your rear is not 4, right, so there is a space available for you to add the element inside your queue, right? Now in this we have two situations. The first situation is whether your queue is empty or whether queue is containing something. If your queue is empty, as you remember, if we go back to this example, okay, if you remember, if your queue is initially empty, you make front and rear both as 0, right? And in all subsequent you only increment your rear by 1, right? So we have to check here that whether our queue is empty, and if our queue is empty, we all know that initially that front will be equal to -1, right? So if our queue is empty, if front is -1, so in that case we will make our front as 0, or you can also write front is equal to front plus 1 and rear is equal to rear plus 1. And in case if your queue is not empty, if your queue is not empty, in that case we are only going to increment our rear by 1, as in case of this example. If your queue is not empty, later on we only incremented our rear by 1, right? And where we are going to scan our element, the element will be scanned at A of rear. The element will be scanned at A of rear. So rear is the end that we are going to use for scanning the element, right? So element will be scanned off at A of rear. Before we do this, if overflow condition is not there, we can ask our user that enter the element. Okay, enter the element. So we can write this statement where user will be entering the element value, right? So this will be not coming here, it will be coming inside our else. Okay. And based on the queue is empty or not, it will scan the element. So I hope you have understood how NQ will take place, which is nothing but our first case of the stack implementation, right? So initially we had focused on this part. If you remember, if our queue is empty, front is -1, make front also as 0, rear also as 0. Otherwise, for all subsequent NQs, only increment rear by 1 and scan the element at A of rear. And when queue becomes full, we are checking this scenario, right? So if rear is equal to 4, then queue overflow. So this is how NQ operation will take place, right? Now let us focus on how DQ operation will take place in this case, right? So for DQ operation, let us take an example. Suppose this is our queue. Okay, suppose this is our queue, and these are our 5 positions: 0, 1, 2, 3, and 4. So suppose I have done NQ, NQ, and NQ. Suppose where will be my front? My front will be here, because for first NQ I make front also as 0 and rear also as 0. Where will be my rear in this situation? My rear will be present at this particular position, right? Now I want to perform DQ. So for DQ, which end we are going to use? If you remember, front end. So this particular element has to be removed, right? So if I print that A of front is DQ'd, what I'll print? I'll print that percentage D is DQ'd, right? And what is that percentage D? That element is A of front. Now after I DQ that particular element, after I DQ this particular element, my front should go ahead, right? Because the next potential element that I will be DQing in that case will be present here, right? So I have to do front is equal to front plus 1. Now this is something different. Here we don't do anything called as -1 as we do in case of stack, right? So for a DQ operation, first we print that percentage D is getting DQ'd and that percentage D is A of front. And further we are going to do front is equal to front plus 1. Further we are going to do front is equal to front plus 1, right? Again, if I ask you to DQ, what will happen? Percentage D is DQ'd. What is that percentage D? It is A of front. What is A of front? It is A of 1. So 20 is DQ'd. And further I will do front is equal to front plus 1. So front will come here. Are you getting this? Now, again if I ask you to do DQ operation, whether DQ will happen? Yes, still my queue has not become empty, right? because still there is one element remaining in my queue, right? So what will happen? I'll be doing dq over here, right? I'll be doing dq over here. So a of front is getting dequeued. So 30 is getting dequeued. And what I'll do? Front is equal to front plus 1. Front is equal to front plus 1. So front will come here. Now a situation you can see here, that whenever you dequeue your last element of your queue, your front is crossing your rear. Now front has become 3 and rear has become 2. So we can say that front has now become greater than rear. Are you getting this? Okay. I again repeat this example so that you'll come to know, right? I had last element remaining, that was 30. And what was the situation? Front and rear both are present at this particular position, right? Now if I dequeue this element, what will happen? A of front is getting dequeued, so 30 will be dequeued. Front is equal to front plus 1, so front will come here, right? So front has come to 3. Front has come to 3. So front is now greater than rear. So now in this case Q has become empty. And if Q has become empty, what we should do? We should make our front and rear both as -1. Now this is not happening automatically, so we need to write a logic for this. It was happening automatically in case of stack, that our top was becoming -1. But in case of Q, if you dequeue the elements, and in a situation after dequeuing, if your Q is becoming empty, it is our responsibility to make our front and rear both as -1. And how we are going to check that? In that situation, your front is going to become greater than rear. So in that case, we will reinitialize our front to -1 and rear to -1. So I'll reinitialize this front and rear both to -1. So I'll make that value. So I'll write logic that front is equal to -1 and rear is equal to -1. Now my Q has become empty, front has become -1, rear has become -1. Again, if I perform dequeue operation, what will happen? Q is empty and user is trying to perform dequeue operation. This is a phenomenon which is called as Q underflow. So this we can easily check that if our front is now -1, our Q is empty, right? And in this case, Q dequeue operation cannot be performed, and this is Q underflow. Now let us write logic for this. So this logic will be written in the form of case 2. Logic will be written in the form of case 2 for dequeue, right? Now if our Q is empty, so front will be equal to -1. Front will be equal to -1. So in this case, we'll print our user that this is the phenomenon for Q underflow. This is the phenomenon for Q underflow. Are you getting this? Now if our Q is not empty, so something is there to dequeue, right? Now that has to be printed first, that what you are dequeuing, right? So %d is dequeued. And what is that you have dequeued? You have dequeued A of front. So you print that 10 is dequeued. What was that 10? It was A of 0 because your front was present at 0. And after you dequeue that, what we did? Front is equal to front plus 1. After we dequeue, what we do? Front is equal to front plus 1. Right? Next time again if I go for dequeuing, so front has become 1. So it will print %d is dequeued. That is A of front. That is A of 1. So 20 will be printed. 20 is dequeued. So front is equal to front plus 1. So front will become 2. Front will become 2. Again I will come here. Right? So front is 2. So it is not -1. It will come in else. So %d is dequeued. That is A of front. That is A of 2. Are you getting this, right? So 30 is dequeued, it will print. So front is equal to front plus 1. Now after doing this, now front has become 3 and rear still is remaining 2. So that check we need to perform here. So after performing the dequeue operation, we should check every time whether front is crossing rear. And if front is crossing rear, we have to make our Q empty. And for making our Q empty, we have to make front as -1 and rear as -1. So how I'll check that? If front is greater than rear, I have to reinitialize my front to -1 and rear to -1. Why we do this? Because Q has become empty. This logic we have written because Q has become empty. Whenever this condition will be satisfied, it indicates that Q has become empty, and in that case front has to be made -1 and rear as -1. This we have to check every time. So how this logic will work? So I'll break this. So when I had 3 elements, that time front was 0, rear was at 2. So I'll come here. Front is not -1. It will come here 10 is dequeued, so front will become 1. Now front is not greater than rear, so it will not come inside, right? Second element will be dequeued, front will become 2, it will not come inside. Third element will be dequeued, front will become 3. Now 3 is greater than 2, that's why it will come inside. Front will become -1, rear will become -1, our Q will become empty. Further, again if I push for any dequeue operation, front has become -1, and that's why it will report me a message that is Q underflow. It will report me a message called as Q underflow. How traverse will take place, the third operation? If we go back in the example, suppose I am in a situation where I have some elements in my queue, right? So if I add some NQ operation, 10, 20, 30, 40, 4 NQs I have done. Will be my front in this case? Front will be present here. Will be my rear present in this case? Rear will be present here, right? So all the contents that are between front and rear are our queue contents. Now sometimes if I dequeue, so front will come at this position, right? So every time my queue will not start from 0. Like in case of stack, everything that was in between 0 and top was our current stack content. But that is not the case with queue. Everything that is between front and rear is our current contents of queue, including front and rear index. So including 1 and 3 in this particular example, right? So let us write a logic for this, right? Now if our queue is empty, front will be -1. So there is nothing to print in my queue. So we have to tell that queue is empty. We have to tell that queue is empty to our user. And if front is not -1, if there is something in my queue to be printed, so we'll use a loop, right? So I'm using a variable I for iterating purpose. So initially I is front, I less than equal to rear, because we have to include both the indexes, right? What will print? Will print the elements one after the other. So %d/n, every line will print one element, that is A of I. That is A of I. And we will finally break this. So this is our case 3 for traverse purpose. What is our case 4? Case 4 is just exit, so we'll write a break. And what is our default option? That user has entered a wrong choice. So we can tell our user, you have entered a incorrect choice. No requirement of break for default. Are you getting this? Okay. So how the logic goes? NQ, DQ, traverse and exit. So in case of NQ, what we did? Q overflow logic. If it is not overflowed, if space is there to be added, again we check whether Q is empty or it is a subsequent insertion, right? So if Q is empty, both front and rear are made as 0. Otherwise only rear is incremented. In case of DQ, first we check whether Q is empty. If Q is empty, Q underflow. If no, if there is something to be dequeued, we first print what is getting dequeued. Then we increment front by 1. After that dequeue, again we check whether there is a possibility that our queue has become empty. So in that case, front will be greater than rear. So we have to reinitialize our queue as empty in that case. So we make front as -1 and rear as -1. In case of traverse, if our front is -1, queue is empty. Otherwise, we print everything from front till rear using the for loop. So let us now compile this code. There is some, okay, we have missed out a semicolon in this case, right? So let us compile this code. Let us execute this. So we have 4 options: NQ, DQ, traverse and exit. Initially if I traverse, it will print me that queue is empty. Now if I NQ, I'll enter the element as 10. I traverse, element is 10. Again if I NQ, 20. Again I NQ, 30. If I traverse, it is printing me 10, 20, 30. Again I NQ, 40. If I traverse, 10, 20, 30, 40. Now if I DQ, which element will be DQ'd? This is Fifo, first in, first out. From 10, 20, 30, 40, the first element that is NQ'd is 10, right? So the element that will be DQ'd first will be 10. So you can see the message, 10 is DQ'd. Now if I traverse, 10 is DQ'd. So what are remaining in my queue? 20, 30 and 40. So if I traverse, you can see now 10 I cannot see, right? 20, 30 and 40. Are you getting this, right? Now again if I DQ, 20 is DQ'd. Again if I DQ, 30 is dequeued. Again if I dequeue, 40 is dequeued. Now queue has become empty, right? Now again if I dequeue, it will tell me queue underflow because there is nothing to dequeue and user is trying to perform dequeue operation. It is queue underflow. Similarly, there is queue overflow also that we have coded, right? Let us try that option also. I'll enqueue 5 elements, enqueue 10, 20, 30, 40 and 50. I have enqueued 5 elements. You can traverse 10, 20, 30, 40, 50. 5 elements I have